Okay, now it's time for a quick derivation with a really intriguing title, Gravity on Other Worlds. I still wish I had chalk sounds when I wrote. Okay, so we want to look at, like, we know G on Earth is 9.8 meters per second squared, right? And we can measure that experimentally. We could just be comfortable to say, hey, it's just that. That's just the way the world is. But you've got to ask the question at some point, why is gravity that value? Like, why is it that number? And it turns out Newton's law of gravitation answers that question. It also allows us to be able to calculate gravity on places that are not Earth. Like, what is gravity on the moon? It's about a sixth of Earth. Gravity on Mars is a little bit less. What is it? What is the gravity on Jupiter? All of these things. Those are the kinds of things we want to calculate. And we're going to derive a general expression. This is actually in your book on pages 192 to 193. If you don't want to listen to me, you can read that. If you don't want to read that, you can just listen to me. You can look at both and kind of follow along. It's up to you. Let's look at a simple situation here. I have a somewhat round circle. Let's say that's a planet, some solid object. Doesn't have to be solid, but it's a little easier to picture if it is. Mass m, and let's say it has radius r. So this is like an actual object. It's not something that's like orbiting. This is a physical object like a planet. And there's a little mass on it, little m sitting on it. We can assume the size of the little mass m is much less than the size of the planet. So essentially the distance from the center of the planet to the center of the object is essentially the radius of the planet. So the distance between m and m is about equal to the radius of the planet, which means we're basically close to its surface and we're a tiny thing in comparison. If, for example, you were standing on a very small asteroid and you were pretty big, like, this might not be a good approximation. You'd have to do something different. But for a planetary-sized object with a person-sized object, or some little thing on it, a cantaloupe or something, it's not really going to be. You can ignore the size. Okay, so here's what we want to do. We know that, like, your force, the force of gravity acting on you, like the pull of that planet on you, for the Earth it's the pull of the Earth or pull of whatever you're standing on, we've written that force, F, as m times g. And on Earth, we know what g is because we can drop stuff and measure what g is, right? So that's how you could figure that out. But and at any planet, if you could go there, you could do the same thing. You could drop stuff and measure g and figure it out. They actually did this on the moon, which is a really cool thing, and it comes out to be what it should be. Okay, but you got to say what gives rise to that force. And what's neat is just because you're standing on the surface of something doesn't mean that a gravitational force doesn't exist between you and it. Like, when you're standing on the Earth, really it's not the Earth pulling you towards it. You and the Earth are exerting a gravitational force on one another. You're pulling one another towards each other. So you attract the Earth as much as the Earth attracts you. And that's hard to picture, that, like, the Earth has a weight on you just as much as you have a weight on the Earth. And those are actually exactly the same number. The force of you on the Earth is the same as the force of the Earth on you, right? Because Newton's third law, every action has an equal and opposite reaction. Well, we now have an alternate way to write the left side of this equation, right? Let's say we didn't know little g. Let's say we're on some exotic planet, planet X. We don't know little g. We want to calculate our weight. We'd like to do mg, but we don't know g. We do have a fancy version for the F, though. We know that's equal to capital G times the mass of the planet times the mass of me, divided by the distance between them, which is, according to this, approximately equal to the radius of the planet squared. That force I can still represent as mg, and notice that my mass cancels out. And I'm left with now an expression for little g on any planet, which is equal to capital G times the mass of the planet, which makes sense. The more mass of the planet, the more gravity it has, divided by the square of the planet's radius. So as the radius gets smaller, without decreasing its mass, that's going to create a more intense g. In other words, a more compact object actually has a stronger gravitational pull. This is why objects, like when stars start to collapse in on themselves, they get denser and denser, but they retain their mass. Their gravitational field intensifies, and in some cases becomes so strong that not even light can escape, and that's what a black hole is. So this is how you calculate g anywhere. So let's say I wanted to know g on the Earth. I would plug in capital G, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared times the mass of the Earth, which is approximately 6 times 10 to the 24th kilograms, so that's not going to come out totally exact, divided by the radius of the actual Earth, which is 6.4 times 10 to the 6 meters. And guess what you get? I'm not going to write it because you know what it is. And if you plug in all the numbers, it'll come out pretty close given my loose approximations. So this is a really useful equation. You can get little g anywhere as long as you know how big the planet is and how massive the planet is. All right, you can even calculate g on the surface of U. It just wouldn't be very much because you don't have much mass. Even though you're small, you're not very massive. So unfortunately, you don't have a very strong gravitational field. All right, guys, see you later.